Right, gents, part 2 of today's session. We're going to have a little bit of a look, brief run through on one type of method of variable speed control for AC motors. We talked last week about the induction motor and how it works, the squirrel cage and everything, and that it's the frequency creates a rotating magnetic field that drags the rotor around and so on. Popular way to achieve speed control with these motors is to use AC adjustable speed drives, or commonly known in trade as inverters. Yeah. Devices have been available for around 20 years and they suit a wider range of applications, from single motor pumps, fans, compressors, to sophisticated machines with multiple drives. So they are very flexible. They operate by changing the frequency of the AC source voltage that we supply to the motor. So they take the AC three-phase supply, or in some cases a single-phase supply, and they convert it into a variable frequency AC supply. They are fairly expensive, but provide a high degree of control, and in many cases reduce the energy used, helps to offset some of the cost. And like all things, as technology moves on, they become cheaper and cheaper, more manufacturers involved with them, they cut their prices, and become more and more cost effective. Okay. The biggest thing is that they allow a precise control of what is generally a standard induction motor. And the advantage there is that not only are they good for new installations, they can be retrofitted in terms of, we've got this motor that doesn't need to run full speed all the time, or don't need to have full power to it all the time, so we can fit an inverter retrospectively to that system. Okay. So, adjustable speed drives can be thought of as an electrical control device that changes the operating speed of the motor. They're able to vary the operating speed by changing the electrical frequency of the input to the motor. What there is, in its most basic form, is an AC input with some kind of converter, an inverter, and then regulating the output to be able to have a variable frequency supply. And we'll look at that in a little bit more detail later. But the most basic way I always describe it is it takes the AC waveform, rectifies it to DC, and then chops it about and recreates an AC waveform, and in doing that the microprocessor is able to vary the frequency of that AC waveform using some quite complex electronics that we're not going to go deeply into, by the way. Okay, so if remembering from last week, if we ignore slip, alright, the speed of an induction motor, so its synchronous speed, can be calculated from 60 times the frequency over the number of pole pairs, that are on each phase. So that formula suggests that we can alter the speed of the motor by either varying the number of poles or varying the frequency. Okay, if we vary the number of poles, all that really is changing the speed of the motor. We can't really do that dynamically. We can't climb inside the motor while going round and stick an extra couple of poles in or take them out. So that's just changing the speed of the motor by changing the number of poles it's got. But varying the frequency, we can do that dynamically, and therefore that's control. It's not just changing it, it's control, and we can do that as the thing is operating. For example, if we got a 4-pole motor operating at 50 Hertz, we'd get 1500 RPM. If we got a 4-pole motor at 40 Hertz, we get 1200 RPM. Okay, so by varying the frequency, we can adjust the speed over a wide range or vary the speed using precise changes of electrical frequency to the input. So we can either have a wide range of different speeds that we can set it to manually, or we can include some kind of sensor to provide feedback and therefore keep the motor at a constant speed with a varying load. That's full control. Okay? So those inverters are flexible enough to be able to do that. Now, there are a number of advantages and disadvantages of inverters compared to other types of speed drive, which include, so we got some advantages. There are energy savings to be had by using inverters. They improve process control. There's an advantage in you get a reduced starting voltage, lower system maintenance. They've got a reasonable bypass capability in most cases, so we'll look at that more deeply, but you can have a normal type starter bypassing the inverter if you need some kind of backup to get it running quickly if the inverter's broken down or similar. And some types, they'll allow you to control multiple motors from the same inverter. The disadvantages are the initial cost of an inverter. Whilst they might be getting cheaper, chances are they cost more than a direct online starter. Low speeds, you get excess motor heating. Again, we'll look at that a little bit more closely in a minute. There's the maintenance issue of the inverter, complex electronics. So your average maintenance engineer probably isn't going to be able to know how to delve into the inverter and repair it if that breaks down. Output harmonics. Okay, so because the AC waveform output is not a per sine wave, it's a recreated sine wave. It includes harmonics, and they can cause issues with the motors and with other things around them. Okay, and also it induces harmonics, or can do, into the power lines that feed it, which can cause issues. So, energy savings. They can be used to save a significant amount of energy in process operations compared to traditional control methods, where the load or the speed of the operation varies. So adjustable speed drives, one of the most efficient ways to do speed control when used on axial, that's a variable torque, loads like centrifugal fans, pumps and compressors. As the motor reduces the operating speed of the fan, pump or compressor, the horsepower required to turn it is reduced. Yep. It's a major advantage of the ASD, one of the primary reasons that they become very popular in process operations, because they reduce their energy required. If we look at a variable torque load, okay, variable torque loads require much lower torque at low speeds than at high speeds. So the torque required varies as the square of the speed, and the power required varies at a rate of the cube of the speed of the motor. So if you've got when the speed of variable torque load is reduced to 50%, the torque required to drive that load is reduced to 25% of what it is at full load. Okay, and the horsepower, or the power required, is reduced to 15% of the amount required to drive at full load speed. Okay, so remember, if that's requiring less power, you've got to put less power in, because you only get out what you put in. So you don't need so much, you haven't got so much going in, you must be using less energy, less watts. Right? Variable torque loads include most centrifugal and axial pumps, fans and blowers, and many mixers and agitators. Okay, so the amount of torque required is going to depend upon the throughput or load you put on the mechanical system that you're using that motor to drive. And in those cases it could well be variable. Yeah. If we look at constant torque loads, they require the same amount of torque at low speeds as at high speed. Torque remains constant through the speed range, and the power increases and decreases in direct proportion to the change in speed. So if the speed drops to 50%, then the power required to drive the operation will drop to 50%, meaning the torque remains constant. So again, we're putting less power in to get the same torque out because we're driving at a lower speed. Constant torque loads include most conveyors, positive displacement and reciprocating pumps, and compressors. Yep. Reduced voltage on starting. Okay, an ASD acts like a reduced voltage starter to limit the amount of inrush current when the motor starts. So you get a lot less inrush current on starting with a motor run from an inverter than you would from a direct online starter. The ASD can generally limit the inrush current to a maximum of 150% of the full load current. And that's quite a lot lower than you would expect to get from direct online starting. Also, improved process control. So solid state electronic device lend itself well to automated process control. This is where we'll have some kind of sensor feeding back information about the speed of the motor to a control part that tells the inverter to add or reduce power to keep the motor at a constant speed or change its speed to some new value depending on what's going on with the process. Okay. So they're quite closely controllable in that sense. They work well with a range of different sensors to be able to keep the motor at a constant speed or react to changes in the system. We need more flow now, speed the motor up. It'll do that quite well. Other types of variable speed control can be very limited as to their interface into a process control system, or they have no capability whatsoever. So dependent, you know, and you may be asked to look at some other types of drive system and how do they compare with inverter drives of induction motors and so on, depending on the applications you're asked to look at. Bypass capability. Many ASD systems make use of a bypass starter in parallel with the drive. It allows the drive to be easily bypassed when critical applications require backup control means. So emergency starting of a system under emergency conditions, you have a starter in parallel that just winds the pump up full speed if necessary. Okay. Other types of variable speed would require physically uncoupled between the motor and load, must be uncoupled, repaired, and then recoupled to the line when there is a failure. So that other systems are less flexible than this in that respect. All right. Also, some designs allow multi-motor control. Okay. So instead of having to have two controllers, the thing's got a smaller physical size than two separate controllers. It would be bigger possibly than one that's just going to control one motor, but smaller than having two separate ones. I've never seen one of them, I have to say. Never even knew you could get multi-motor controllers, but you learn something every day, as they say. Disadvantages, okay? They aren't the best choice for all variable speed applications. There are some drawbacks. And those drawbacks are generally advantages to using other types of speed controllers. As follows. Disadvantage, the initial cost. Generally greater than other types of variable speed control. Yeah? But payback from energy savings has traditionally been used to justify installation. However, improvements in process control are increasingly being considered instead. The energy savings payback is generally low for applications where the average speed requirement is near to the motor's rated speed. So these energy savings we're talking about only happen if the motor's got a considerable time running at less than its rated output. If you're going to be running at synchronous speed, there ain't a lot. You're not going to get any energy saving. As a general rule, a payback of 2 to 3 years typically justifies the use of an inverter. Okay. Maintenance. Like many other solid-state electronic devices, requires special troubleshooting knowledge for operations and maintenance personnel. So we're talking about going inside the inverter and finding out what's wrong with the damn thing. The average maintenance engineer probably ain't going to have the knowledge or the equipment to be able to do so. So in that case, you're going to want to be carrying complete inverters as spares so that you can swap them over. Yeah, or have a bypass solution. Yeah. They do have a lot of them diagnostic capability, but again, that could require additional training to be able to understand that. And in my experience, the manuals for these things are like trying to read, the Bible type. They're not always particularly user-friendly, as it were. Okay. Motor heating at low speed operation. ISDs used to run constant torque loads at low speed have a high potential for motor overheating. No matter what speed the motor runs, the current drawn to the motor will be the same with a constant torque load. Yeah. So if you're running it slow, these induction motors are usually cooled by a fan on the end of the shaft. So if it's running slow, that fan's not pushing so much air through the motor, and therefore it's going to get hotter than it normally would. If the motor produces the same amount of heat at low speed due to the constant torque, then the less cooling air will mean the motor will overheat. As a rule of thumb, you can generally take a fully loaded Class B insulation motor down to 50% hit speed on constant torque loads without overheating. The issue's not there so much if your torque is going to reduce when you reduce speed, because then that's not going to get so hot anyway. It's going to be drawing a lower current. You can generally take a fully loaded Class F insulation motor down to 20% of its rated speed without overheating. If you want to run it any slower than that, you're talking about derating the motor. In other words, you have to install a bigger motor than you normally would to take account of the overheating factor. Right? Now, industry anyway, I thought you might like. So, let's move on to a blank screen. Another disadvantage is the output harmonic distortion. The output electrical waveform generated by the ISD is not a pure sine wave. It includes harmonic distortion, which is supplied to the motor. All right. These harmonics, and I don't know about Brownie, but you know about harmonics. We've done that in electrical principles. So they're multiples of the fundamental frequency. Any waveform can be said to be made up of a number of a fundamental and a number of harmonics. These harmonics can cause with a current component, and a current component will create heat in the motor. So we got extra harmonic currents flowing, and then we got this issue of if we get a resonance with one of the harmonics, we can get some big voltages or large circulating currents set up. So they aren't a good idea. As a rule of thumb, ISDs will create between 5 to 8% extra heating in a motor compared to the same motor running on a per sinusoidal waveform. One way to overcome this problem is to use a motor with at least class F insulation or an inverter rated motor with a class M insulation. So we're talking about the extra heat being more likely to break the insulation down. Okay. Induced power line waveform distortion. So a solid state electronic load causes waveform distortion to be induced on the input electrical power supply, which is effectively the national grid. Yeah. Waveform distortion created by ISDs consists of both harmonic distortion and what's called line notching. Harmonic distortion and line notching are the result of non-sinusoidal waveform the drive generates, which pulls the current of the power line in non-sinusoidal pulses. So instead of the current, if the voltage being supplied is non-sinusoidal, the current it draws will also be non-sinusoidal. Yeah. This can severely distort the electrical power supply within the facility, and if not properly protected, can hinder the operation of other devices. Operations using ISDs in the vicinity of sensitive electronic equipment should consider including either an isolation transformer or line reactors on the input of the drive to protect the other equipment from this potential problem. To installing additional equipment to protect other sensitive equipment from the harmonics created from these drives. Yeah. I ain't got a clue, Joe. Should we try and find out?
Yeah.
I'll leave you to find out between now and next week.
When you say we, you mean you.
You, for the collective we.
Yeah.
Yeah, Jill's going to tell us what a line reactor is next week. Alright? Okay. And one of probably the most common way for this sine wave to be recreated by the electronics is, remember we're looking for that, yeah. And what the inverter does is recreate that using pulse width modulation. So it'll send out a square wave where the pulses get wider when you want the voltage to be higher. Like so. I'm not very good at drawing that, but the pulse width gets bigger when you want it to be higher. So you don't end up with a perfect sine wave, you end up with a notchy one, like you saw on the diagrams before. Yeah. Or they can do it by pulse frequency. So they'll vary the frequency of the pulses. So if that's going, they're very tiny little short pulses, but they'll zap out faster or slower, and the average voltage over that small period of time will depend on how many pulses there are in that period of time. But we're talking megahertz and higher of the frequency of that square wave. The issue there is, can we get it up and down fast enough? So all this is quite complex electronics. That for this module, we're interested in the application of these drives rather than how they work. Yeah, how do they compare with, let's say, stepper motors or reluctance drives or other forms of drive, rather than how they work. Will you find out, Daniel? All right.